Now we go straight to the derivatives of inverse trig functions. So we are trying to figure out the derivative of arcsine u, and we let y be equal to arcsine u, and we know that it means that if we make u the subject, then it would be equal to sine y. Then we find the derivative of the expression u equal to sine y. On the left, we have du over dx. On the right hand side, we have cos y times dy over dx using the chain rule, because both u and y are functions of x. We make dy over dx the subject, giving us 1 over cos y multiplied by du over dx. And then we want to replace cos y with an expression that has got sine y, because we already have u equal to sine y. Then we use the identity sine squared y plus cos squared y equal to 1, and make cos y the subject. And then it gives us the square root of 1 minus sine squared y, where sine y is equal to u. Then we substitute. So it means we'll have dy over dx equal to 1 over the square root of 1 minus u squared multiplied by du over dx. Therefore, because we had said y is equal to arcsine u, it means then the derivative of arcsine u can be given as 1 over the square root of 1 minus u squared multiplied by du over dx. We can use this format to prove also the derivative of other inverse trigonometric functions. If we continue like this, we can then be able to find the derivative of arcsine of 4x. Remember, now in place of u, we have 4x. So we know that we'll have 1 over the square root of 1 minus u squared, which is 4x all squared, multiplied by du over dx, which is the derivative of 4x, which is 4. Also, we can be able to prove now the derivative of arc cos of x, or should I say arc cos of u, and arc tan of u. The derivative of arc tan of u is 1 over 1 plus x squared. Or should I say arc tan of x is 1 over 1 plus x squared. The derivative of arc cos is the same as the derivative of arcsine, but we just introduced a negative. So if it's a cos of u, it means you'll have minus 1 over the square root of 1 minus u squared multiplied by du over dx. That is why we have example 2. We're asked to find the derivative of 2 arc cos of the square root of 2 minus x. The derivative of arc cos is the negative of the derivative of arcsine. So it means we take the 2 out, and then we have the negative of 1 over the square root of 1 minus u squared, and in place of u, we have the square root of 2 minus x, multiplied by the derivative of u with respect to x. That means we're differentiating the square root of 2 minus x, which is 1 over 2 square root of 2 minus x multiplied by the derivative of the argument of the square root. So note this, the derivative of arc cos is the negative of the derivative of arc sine. If you keep that in mind, then you've got it. Derivative of arc sine of u is 1 over the square root of 1 minus u squared multiplied by d over dx, and the derivative of arc cos is minus 1 over the square root of 1 minus u squared times d over dx. Then number 3 introduces now us to the derivative of arctan. Note once again, once you have the derivatives of inverse trig functions, anything can or any expression can be given. Now we find ourselves with the product rule that has incorporated arctan. So we need to use the product rule for the first term, and we know the derivative of minus x, we know it's just minus 1. So product rule, differentiate x squared plus 1, it gives us 2x, and when you multiply that by arctan of x, plus x squared plus 1 times the derivative of arctan, which is 1 over 1 plus x squared, and we have that negative 1. Also, number 4, product rule for the first term gives us arc sine of 2x plus x times 1 over the square root of 1 minus 2x all squared times the derivative of 2x, which is 2. That is why we have that expression, plus half times the derivative of the square root, we know it's 1 over 2 square root, multiplied by the derivative of the argument of the square root. So note, I'm hoping you're noticing the chain rule comes in, product rule comes in, and you'll realize that quotient rule also comes in. Sometimes we find ourselves having to use implicit differentiation and log differentiation depending on the expressions that have been given unto us. So for now, we'll just deal with arc sine, arc cos, and arc tan, but there are other derivatives for arc cosec, arc sec, and arc cot that have been given in your rules of differentiation. We go to example 5. Note that the chain rule had to come into play, where we first had to find the derivative of the square root and then multiply that by the derivative of the argument of the square root. Please check to see whether everything has been done appropriately and if the answer is correct. Also, we are asked to find dy over dx for number 6. I'm hoping you're noticing B, where you're supposed to find dy over dx, and now actually even in A we have been given implicit expressions. So please make sure that you are apply all the rules for implicit differentiation to find dy over dx, especially for 6a and for 6b. Product rule for 6c. More exercises. Number 1, you are asked to prove those. So we have to apply appropriate identities. For the first one, number 1a, sine squared theta plus cos squared theta equal to 1 will work, and then you need to figure out what identity will work for arctan. And then we once again find dy over dx for number 2, where some problems have got quotient rule, some problems implicit, some we just use straightforward chain rule. please do these exercises and make sure that you check your calculations and your simplification. We go straight to hyperbolic functions and their inverses. Here is a table. Note that the derivative of sine x is cos x, and the derivative of cos x is sine x, but the derivative of tan x is sec h squared x. The derivative of sec h x is negative sec h x tan x, and the derivative of cosec hx is negative cosec hx tan x. So I need you to note the differences between the straightforward trig functions and the hyperbolic functions and their derivatives. And also note the derivative of the inverse hyperbolic functions compared to the inverse trig functions. We'll use this as we move. Some identities for hyperbolic functions that are useful. Please take note of them because they may be useful. And also the definitions of some inverse hyperbolic functions that will prove to be useful as well. Let's do some examples. The first one is to prove that the derivative of arcsine x is 1 over the square root of 1 plus x squared. Exactly the same thing that we did for the inverse trig function. Let y be equal to arcsine of x, and then it means x is equal to sine y. Find the derivative of sine y equal to x using implicit differentiation and chain rule. So the derivative of sine y will then be equal to d over dx, which is equal to d over dx of x. And then we have the derivative of sine y, we know is cos y times dy over dx equal to 1. And then that means dy over dx is equal to 1 over cos y. Then we use an identity that is appropriate, because remember we had said x is equal to sine y, so our expression for cos must have sine. Then we use the identity cos squared y minus sine squared y is equal to 1 and make cos y the subject. And then we substitute. So we ended up with 1 over cos y being 1 over the square root of 1 plus sine squared y, and in place of sine squared y we substitute x. So that means the derivative of arcsine of x is just 1 over the square root of 1 plus x squared. The other method that we could have used, we could have used the definition of arcsine x, which is ln of x plus the square root of x squared plus 1. Find the derivative of both sides because we're just looking for the derivative. The derivative of the right hand side is 1 over the argument of ln multiplied by the derivative of the argument of ln. So find that derivative, we get 1 plus 1 over 2 square root of x squared plus 1 times 2x. Simplify. Simplification leads us to the same answer. Please check that simplification to see if you are going to get the same answer. Then number 2, we are asked again to find the derivatives of the given expression. We have now arctan of sin x. So we use the chain rule. First, find the derivative of arctan. We know it's 1 over 1 minus the argument of arctan squared multiplied by the derivative of the argument. Simplify and we get sec x. Please check the steps. Make sure that we use the correct derivative of arctan. And then B also still has arctan, but it's x of arctan x plus ln of the square root of 1 minus x squared. Product rule for the first term gives us arctan x plus x times 1 over 1 minus x squared plus the derivative of ln of the square root of 1 minus x squared is 1 over the square root of 1 minus x squared for ln multiplied by the derivative of the argument of ln, which gives us 1 over 2 square root of 1 minus x squared times negative 2x. And then you simplify and you discover that your final answer is just arctan of x. Please check the simplification and see if you're going to get the same answer. Here are some extra exercises that require your attention. Please practice, practice, and practice some more. Straight to higher derivatives. We can move from first derivative to second derivative to third derivative and more. The expressions for the second derivative is of y with respect to x is given by d squared y over dx squared, which is f double prime of x, or sometimes we use d squared x of y or y double prime. So please check the notation that we are using, even for the third derivative. So if you've got the first derivative, you differentiate the first derivative, you get the second. You differentiate the second derivative, you get the third, and so on. So let's do some examples and let's see. The first example requires us to find the second derivative of the given expressions. We have a being y equal to x cubed plus 1 all to the power 2 over 3. The first derivative, please check with me. Remember, you will have 2 over 3 multiplied by x cubed plus 1 all to the power 2 over 3 minus 1. 2 over 3 minus 1, so it gives us negative 1 over 3 in that power, multiplied by the derivative of x cubed plus 1, which gives us 3x squared. Now, in the denominator, I need you to check whether the simplification gives us the same answer. Check if you get the same answer. Then we go to the second derivative. We differentiate that. That means we now use the quotient rule. Check whether your differentiation of the first derivative will also give you the given answer. Please check and make sure that you are thorough and accurate in your simplifications. We go straight to B. As you can see, it's a product of two functions, so we use the product rule. Please, once again, check if the use of the product rule has been implemented properly or has been done properly, and also now differentiate G prime to get G double prime and see if you're going to get the same answers. Then we go to C, x cos x, and I got cos x minus x sine x because of using the product rule. And then from there, I use straightforward derivative of cos x and the product rule for x sine x. Check if you're going to get the same answers. So if your first derivative is correct, it makes life easy for you to get the second derivative. So make sure that every time you do your differentiation correctly and your simplification, and check, please check. D, now we get complicated because now this is also applicable for implicit differentiation. X to the power 4 plus y to the power 4 is equal to 16. That's what we have been given. So we use implicit differentiation and chain rule. X to the power 4 gives us 4x cubed. Y to the power 4 gives us 4y cubed times y prime. And the derivative of 16 gives us 0. We make y prime the subject. So note your formula for y prime is negative x cubed over y cubed. Now, finding the second derivative, you are differentiating your first derivative answer using quotient rule. Please check if it has been done appropriately. Simplifying the third step of the second derivative, that's what I got. Note that now I found myself with y prime also in the expression for the second derivative, and already I had an expression for y prime. Substitute y prime in and then simplify. Please check whether you're going to get the same answer as I got there for the second derivative of y. So when we are looking for the second derivative, note that you may encounter a situation, especially for implicit differentiation, you'll encounter a situation where you'll have to substitute the expression for y prime and simplify. So make sure your y prime expression is correct. E, we use implicit differentiation again. Let's see. So differentiating each term and make y prime the subject. Then differentiate your y prime using quotient rule. Note that you end up with y prime in the first term. Substitute the expression for y prime in and simplify. The answer I got is the square root of x divided by 2x squared. After simplification, please check if you are going to get the same. Check each step, please. Number 2 of the exercises is asking us to find the third derivatives of the given expression. So now, after finding the first, you get the second. After finding the second, you get the third derivative. And you do, so it's very important that your first derivative has to be simplified to make it easy for you to find the second derivative. After finding your second derivative, simplify it so that it is easy to go to the third derivative. So please check your evaluations, check your simplification, and make sure that you've used the correct expressions for each derivative. Number 3, I just gave you some few examples where now you are not asked which derivative we are looking for. We're just asked to find a higher derivative. Higher derivatives. That's what you've been asked for. So you find all the derivatives until you get to the derivative that gives you a 0. And then you conclude that y, the nth derivative of y is equal to 0 for all n greater than or equal to that derivative or that number that gave you a 0. In this case, we had y prime equal to 15x squared minus 2x. The second gave us 30x. The third gave us 30. The fourth derivative, note the notation. The power of y is in brackets to show that it is a derivative. The fourth derivative gave us 4. And because the fourth derivative gave us 4, we know all the other derivatives. Fifth derivative will be a 0 also, all of them. So then we are able to conclude that for all n greater than or equal to 4, the nth derivative will always give us a 0. Let's do one more. Let's see. We go to B. B, we have y equal to x into x squared minus 1 all squared. For me, I would simplify y and write it out as a polynomial. I can see that the highest power of x will be 5. So I'll have a polynomial of the fifth order, then find all the derivatives, until I get to the derivative that will give me a 0, and then conclude. For number 4, we're asked to find the second derivative at the value x equal to negative 2. So that means you find y prime, find y double prime, and then substitute negative 2 into the second derivative. Number 4, now it includes expressions that are implicit. Implicit differentiation is required for number 4. So, and we're asked to find the second derivatives. Remember what we did was that we ended up with y prime as part of the expression for the second derivative, and then you substitute your y prime in, and then you do your simplification for the second derivative. So don't forget that. So these problems, they get a bit complicated, but be patient with yourself and be diligent and be accurate in your evaluations and simplifications.